Early in the game, whether you know it or not, you've been hearing that the atmosphere and its dynamics is three-dimensional. And a lot of what Ken talked about was surface with some implication of what might be going on aloft. Structure of what's going on aloft, very important, what goes on at the surface. And we get that information from the 500 millibar chart. And we're really fortunate today to have with us Lee Chesneau. Lee is a well-known instructor, runs courses, teaches at MyTags, teaches at the Star Center down in Florida, is a regular at boat shows, a meteorologist from the Midwest. He has Navy experience, served in the Navy. He had commercial routing experience, and he worked for
Ocean Routes?
No, the number of years at the National Weather Service. In the days up to the Ocean Prediction Center and the Ocean Prediction Center. So we're very fortunate to have with us Lee Chesneau.
Well, good morning, everybody. Bright-eyed and bushy-tailed, welcome to MyTags. This is really a special place for a number of reasons, as is Star Center, because all the products that you're hearing about, seeing, and trying to understand had its foundation here at this school, just 30 miles away at the time was Camp Springs, Maryland, and it could have easily been the Star Center if the two locations, Dania Beach versus Lithicum Heights, were reversed. So the charts that you're going to see throughout the day have been Mariner originated, for the Mariner, of the Mariner, by the Mariner, and it's the one part of the government that's really working today, and that's your National Weather Service. Do you know, for less than the cost of a Big Mac, that's the cost for your weather services, just the cost of your Big Mac, your tax dollar. So we're fortunate to have Joe Sinkowitz here today, who's going to keep us up to date with the latest. And I'm going to keep you up to date with training, the importance of training. Before you leave here today, please take a little gander at the hallway and see the plaque of commemoration of the tragic loss of 33 souls on El Faro. Nobody that takes a course from me, and Ken for that matter, and do we have Captain Kathleen Frail in the audience here? Okay, well, she's one of the instructors along with Ken that teaches at the Star Center. Kathleen Frail, how about Bob Kimball? Is he here? Okay, both of them are captains. They've been here throughout the course of the day, and you get a chance to have a chat with them because they understand the importance of weather, and they understand the importance of human intelligence. And we live in the world of artificial intelligence, the digital world. Red is bad, blue is good at, and what the hell else you need to know? Well, you need to know a lot more because the symbology on these charts do matter. The difference between rain and fog versus squall line producing thunderstorms, all the symbology. Here he is. Bob, you want to at least raise your hand and be recognized? Bob Kimball, captain, who was a classmate of Joe Sinkowitz, by the way, and who happened to major in meteorology, and he also took a career path similar to Joe's, except he operated on a big ship. So, why the 500 millibar? Imagine if I took a blanket and cast the entire room with a blanket. To an observer watching this unfold, what would you see? Other than maybe a shape of a pinhead or a blockhead? I'm going to let you guys figure out what else is in between. What does that really mean? If I lay a blanket and you see these peaks and valleys on a otherwise flat surface. So we're talking about 500 millibars. The level in the atmosphere where surface weather dominantly, especially in the mid-latitudes, is controlled by. So it makes sense to understand cause and effect. So This is a typical summertime map, surface map of the Pacific West Coast, and it's not uncommon to see a gale box, a low in the interior, and a whole bunch of isobars running north-south to give us our strong northerlies from Cape Point St. George all the way down to Point Arena, sometimes even further south to Point Conception. This is typical. So you have the Transpac race, you have the Pacific Cup, and the Vic Maui race, and it's all about strategizing to the Pacific High, as they call it. And where's a knuckle to make the turn toward Hawaii? All the West Coast races are to Hawaii. So this is typical summertime. Now we happen to have in the audience a navigator extraordinaire by the name of Ralph Naranjo, who's going to talk a little bit later. And I'd like to ask you a question. I think you're familiar with West Coast weather. You've been around a little bit. So does this look typical for weather along the West Coast in July?
Yes.
In what way?
Well, you have a low that's forming due to the heat. You have a high that's Central Pacific, and you're going to be getting around the high without entering the center of it.
Except here's a problem. What's that doing there? I mean, you're low in the interior, you'd expect that, but why would that be there?
Well, you're seeing the anomalous low that's moving off north of Point Conception.
Well, close enough. Here's the deal. This is a south wind, southwest wind, two ship reports in vicinity of one another, and this 3-dot symbol means moderate rain. That's not necessarily typical in San Francisco. So I had some hotshot Stanford graduate with a PhD, a big-time sailor, and he was scratching his head. We're not supposed to get this. What's causing it? So he asked me about it, and then I said, I'll look into the archive and see what I can find, because that looks strange to me too. This is what you normally expect. The low is inland, and the winds are strong on the northerly winds all along the West Coast. So the only way you can get something like this is to have something like this. That's not normal. That's an upper level, Ralph, what do we call that? Cut off low. Thank you very much. So, do I have your attention? You just can't rely only on surface weather and expect to understand why things are the way they are, especially when you have anomalies like this. So, why should you care about the 500 millibar chart? So here is Ralph Naranjo's quote. The 500 millibar chart is key that unlocks the three-dimensional nature of the atmosphere and helps answer the mariner's two important questions. Will the system intensify, and where is it heading? And then you have my co-author, Molly Chin, known as Captain Mike. Regardless of sea-going purposes, it is our goal to see any navigator on the high seas, that's any navigator, whether it's big ships or small vessels. If you're going offshore, this applies to you. Start on your own journey using the 500 millibar for safety, strategic navigation, and improve self-reliance in weather forecasting. The key word here, self-reliance. In the end, who's responsible for your weather forecasting and routing decisions? You have a wonderful representative in Ken McKinley and Ken Campbell. They will tell you, they advise. They advise. They don't tell you what to do. They give you their best shot at what's going on. In the end, if you're a weather-wise sailor, you will understand what they're telling you that makes sense, and then you can apply it to your own vessel, because after all, who knows your vessel more than you do? You're out there, and the two Kens are on shore, like I used to be. And I learned a lot when I worked at ocean routes in terms of how mariners, especially captains, felt about shoreside recommendations. I'll talk about that over a beer, not here. So, a little bit more. This is about gaining the big picture. An invaluable opportunity to avoid heavy weather, and that 500 millibar holds the key to that understanding. So, our objectives in this really condensed version and it will be condensed, and I'm going to go fast, and this is about what you know versus what you don't know versus what you need to know. So if you can follow me, great. If you can't, you're going to have to do something about it. So upper air constant pressure surfaces versus constant altitude surfaces. How do we use constant pressure surfaces? The rules of thumb. If something happens over and over and over and over again, what's your logical conclusion? My professors in college would say 999 because I had a lot of Germans for my professors, and they were adamant in terms of understanding differential equations, of which I never want to see another one in my life. So, rules of thumb as applied to the surface. So, why the 500 millibars? When your boat is at sea level, 500 millibars is halfway up the atmosphere. So, Ken's discussion this morning, maybe he mentioned the average pressure at sea level. Anybody know that? 1013.2 millibars. So we're halfway up the atmosphere as we evaluate what 500 millibar is. Okay, so then we're going to talk about jet streams. We all heard about jet streams, and they've gotten real fancy over the years. The polar vortex, for example, and El Nino and La Nina. These are all part of global jet stream patterns that we'll allude to in this short segment. Troughs and ridges are common on the surface. Troughs and ridges dominate 500 millibars as well. Now, some of these troughs and ridges take on the shape of long waves and short waves, so we'll touch upon that. Vorticity concepts. I'll briefly mention that. That is really the science that goes into these troughs that work the dynamics and creating surface lows, and in some cases highs when you're talking about negative vorticity versus positive vorticity. Technical terms, but you're going to see a lot of vorticity in the Olympics. What is vorticity? Spin. And you're going to see a lot of the skating doing a lot of spins. They're creating vorticity. And of course, why the 500 millibars if you can't relate it to the surface? All right. So, weather is a three-dimensional system. Ken alluded to this. You cannot get surface highs, lows, highs without the upper level dynamics of convergence aloft to give you high pressure, divergence aloft to give you low pressure, and on and on and on. So you see, we're talking about a fluid. The atmosphere is a fluid. So all the laws of fluid dynamics apply. Conservation of mass, conservation of momentum. You take away from one area, you have to add it to another. So this is three-dimensional, and it's all simultaneous. So, a quick review of the surface map, which you should be familiar with because that's where your boat is. So when you look at isobars, remember Ken's discussion, 2 digits, rounded off, so to speak, beginning with 1,000 millibars, and each interval spacing is every 4 millibars. Okay, you have your highs, underlying 4 digits, and is it possible to get a 999 millibar high? Is it possible to get a 999 millibar high? Of course it is. It's all about what pressure surrounds it. So remember what the H's and L's represent on a surface map. So all these different symbols, and you have to keep in mind when we're dealing with ship reports, that's a different perspective here in terms of interpretation. We won't get that in this particular segment here. So reading the surface map is your comfort level because that's where your boat is. Okay, we have different levels in the atmosphere once we leave sea level, where the average pressure between the poles and the equator is 1013.2 millibars. Up we go, and what happens to your pressure? Decreases. Less weight being exerted on the surface. So these constant pressure surfaces have value to somebody. I like to think that 850, the rain versus snow, we experienced that a lot in the DC area when I worked here a number of years ago. I guess it's 11 years and 6 months and counting. At least one of us in the audience is certainly that, and now I am. Because here's the deal. It doesn't matter whether you're a commercial mariner or a recreational mariner, weather needs to be understood equally. Platforms are different, strategies are going to be different. So every one of these surfaces has some value. I picked 500 millibars And most forecasters do because it drives the surface storm track. It's movement, decay, and development and intensification. This is a very key level. So in flying from Seattle, where I'm from, 300 millibars, 200 millibars, the aviation industry is highly interested in that. It took me an hour and a half quicker to get here. When I go home, it's going to take me an hour and a half more because most of the time there's high winds at upper levels, like 200 and 300 millibars, run from west to east. Okay, so each one of these pressure surfaces has some use. We're going to focus this morning on 500 millibars. So why constant pressure surface versus constant altitude like sea level? Denver, Colorado, the mile-high city, has to be calibrated at sea level. The barometers on ships need to be calibrated at sea level. So we're measuring constant altitude. We're looking at pressure differences, high pressure and low pressure. When you're dealing with upper levels, you're looking at essentially the basic fact that all the equations used in modeling work best on constant pressure surfaces. So we have variable altitudes on the same pressure here. So it's like a geologist contour relief map. So let's take a look at this constant pressure surface and see what we're dealing with here. You're dealing with what we call iso heights. Iso meaning equal, and height in reference to elevation. So 500 millibar heights with this 587, and I don't know why the computer geeks did this, but for the next 30 days, because that's when the shrinks say it takes to develop a habit, add a 0 to every one of the numbers. And you will be looking at these charts every day. Everybody go like this. So if you stop at 29 days, guess what you have to do? You got to start all over again. So add a 0 to every one of the numbers, and you have the heights in meters. So on a surface pressure map, the spacing of the isobars again, how many millibars? 4, traditionally 4. On the 500 millibar charts, you're looking at the mountaintop and yielded into the valley at 60-meter intervals. So each one of these iso-height contours are 60-meter intervals from higher to lower and vice versa. So you're at the mountaintop, you have a barometer strapped to your vest, and you're yodeling into the valley at 60-meter intervals. So you can do the math in terms of what is the height difference between 5,870 meters and 4,110 meters. And I'm not going to do it for you. It's somewhere about 700 and something meters. And your pressure is always going to be 500 millibars. That's not going to change. So the winds that you see on this chart, the winds that you see are every 5 degrees of latitude and 5 degrees of longitude, provided it's greater than 30 knots. Anything less than 30 knots is not plotted. And it is geostrophic, essentially. And Ken covered that earlier this morning. So in many ways, the iso heights are similar to the isobars. The closer the isobars, everybody, the stronger the winds, the further apart. And the same is true at 500 millibars. Okay. So every one of these contours are separated 60 meters apart. You're looking at heights that are plotted in decameters. You have to add a 0 to have full meters here. So this is how to interpret iso-height elevation. Now, cold air is heavier and denser than warm air. Cold air tends to contract, and warm air tends to expand. So the height of a given pressure, such as 500 millibars, is going to be lower in cold air, and the same pressure, it's going to be higher in warm air. So you can look at some of these elevation contours going from low latitudes to high latitudes. Naturally, one expects the air to be colder. So the heights, as you go higher in latitude from lower latitude, are going to drop. So when you're looking at an H and an L on a surface pressure map, that means high pressure and low pressure. When you're looking at an H on a 500 millibar chart, that's high altitude. And when you're looking at an L on a 500 millibar chart, that's low altitude. So don't call it low pressure, high pressure. When you're dealing with 500 millibars, call it what it is. Upper level high, upper level low. And reserve the word pressure for sea level. Okay. So this is an example going from lower latitudes to higher latitudes. 5,700 meters, 5,460 meters, 5,220 meters. So the further north or the further in latitude you go, the lower the heights on a 500 millibar chart. So again, just briefly with the winds, everybody should be able to interpret winds. Remember, this is not at sea level, everybody. This is at 500 millibars, and I get in the classroom all the time, and they keep calling, look at those strong winds. They're not on the surface. They think it's on the surface because their frame of mind is at sea level. You switch to 500 millibars, you gotta switch your total concept of viewing these charts down from space. You're looking down from space, and this is the mountaintop, and this is your valley. Again, winds of less than 30 knots are not going to be plotted. This is every 5 degrees of latitude and every 10 degrees of latitude. So this is exactly the way you need to be able to evaluate winds on a 500 millibar chart. Note, by the way, everything is rounded off to the nearest 5 knots and 10 knots. The range, their actual range can be 2 knots either side. So 33 to 37 knots, 35 knots fits in the middle. If it's 32 knots, then you go into 30 knots on a wind barb. So there is a little bit of wiggle room in terms of the range of winds in looking at these wind plots on all charts, including surface pressure maps, that's surface forecasts, because on surface pressure analyses, you're seeing real-time observations. So this is all calculated based on the nearest 5 and 10 knot intervals here. So, troughs and ridges. We know about that on surface maps. What about 500 millibar charts? How do we determine troughs and ridges? Well, you have to estimate. Based on the dip of the isoheights and the curvature, this is dipping toward the equator. This is also showing cyclonic air motion. Cyclonic about what? Cyclonic about a trough axis. This is anticyclonic or clockwise motion about what? About a ridge. So the ridge serves the purpose to indicating strong wind shifts from one direction to another. Anticyclonically for a ridge, cyclonically for a trough. Again, an H and an L on a 500 millibar chart is elevation relative to the nearest isoheight. So you can have an H and an L next to each other. The computer has been programmed, I believe, you can correct me if I'm wrong, Joe, if it's 30-meter difference, it might stamp an L or an H nearby. This is black and white. Good old HF single sideband, the dominant method in receiving information at sea graphically is in black and white because Jim Corman's going to tell you why. I'm not going to steal his thunder on that, as everybody knows that you're able to receive black and white at sea versus color. So if you don't have high-speed internet, this is the type of chart you should be seeking. This is all black and white, and a little bit more difficult to determine where the troughs are, a little easier here, a little harder here. And we'll tell you why as we go along. So, putting upper air together in terms of how it relates to the surface, your upper level lows and trough axes as it was put back a few years ago. And this is the way it looks today. You compare the upper levels and the surface, and there's a match here, because even though we're dealing with weather at halfway up the atmosphere, when you see an L or an H, there's going to be some kind of surface response. And yes, indeed, upper level lows correspond with surface low pressure systems. Upper level highs correspond with surface high pressure systems. The big thing that you have to understand, there is a vertical disparity sometimes between where the upper level low is and where the surface low. But believe it that they're all interrelated, because you're looking at two-dimensional display of the weather. So you're very, very smart into this symposium, because the process of thinking three-dimensional should well be underway here, because that's what weather is. It's a three-dimensional system. So surface lows are located usually to the right-hand side of a 500 millibar chart, axis of maximum vorticity, as it was done a few years ago. It's being done a little differently today. So, are they related? Thank you, Joe Sinkowitz, for this animated graphic. And what you're looking at is the yellow is in isobars, the white is in isoheights. It's been programmed for 30 meters and 2 millibar isobar spacing, but you can see how the surface and the upper air are absolutely related, and what you're also seeing is the dynamics of explosive deepening. And the reason for that is the upper level dynamics is helping feed that. You must have upper level divergence aloft in order to have low pressure on the surface. You must have upper level divergence aloft in order to have low pressure on the surface. And here's another older version. Wait a minute. Yeah, this is going fast. Your technology's quick for me. I know you want me to keep on time, Frank. So, a few years ago, when I was on active duty with Ocean Prediction Center, we're able to overlay multiple sources of information. So this has been simplified between red as isoheights and yellow as isobars. And you can pick an area and see how closely they're related. So this is a time frame of every 3 hours. We're going to focus on East Texas here. So we need to get ready now. So we're starting in 0 hour, and here's a 500 millibar trough that we call in the digging phase, and you're going to hear about the rules of thumb, parallel to the isoheights at 1/3 to 1/2 to 500 millibar winds. So there are rules of thumb that will help you understand the 500 millibar as it relates to the surface that I'll discuss with you in a little bit. So, 500 millibar charts describe because it dominates surface weather. 500 millibar controls and dominates surface weather. Professional forecasters and mariners can use the 500 millibar charts to determine where a surface low pressure systems develop, decay, and the direction and speed of motion. Surface wind conditions can also be derived from 500 millibars, not everywhere, but as you know, winds are a primary generator of sea state, so certain areas on a 500 millibar chart will tell you what kind of winds you're going to have on the surface. Initial route planning and underway diversions. Does this apply to a smaller 5-knot sailing vessel? Originally, when I wrote my book with a co-author with Captain Molly Chin, I didn't think that this would be more over the head of recreational boaters, and I'm finding out more of you have embraced this than professional mariners themselves. Yes, indeed, I had my School of Hard Knocks early in my career when I worked for Ocean Routes. 7 days on the job, I was called into the office to see what I knew about 500 millibars, and they knew I didn't have the answers. So they wanted to know, looking at a 500 millibar chart, what iso height is going to cause rain in San Francisco, because that's where I worked, in San Francisco. I didn't have a clue. And so he said, all right, if you want to work here, you need to pass a quiz in 2 days, because if you don't answer the quiz, we're not going to invest any more time in you. So for the next 48 hours, I took this white paper, and obviously they had no intention of doing that, but they wanted my undivided attention, how important 500 millibars in terms of routing vessels, because that's how they did it. And then a few years later, thanks to my tags, the biggest company that the Ocean Routes had was American Crescent Lines. And way back when Glenn Payne was teaching the course, they basically wanted the masters to come here, and they forced Ocean Routes to come up with a white paper so masters can learn to use the 500 millibar to reinforce what the routing recommendations of Ocean Route was. And so no longer a trade secret. No longer a trade secret. So here are your rules of thumb. Surface lows will track parallel to the isoheight contours aloft. Surface lows track at pardon the spelling, we can get that fixed. Surface lows track at 1/3 to 1/2 to 500 millibar wind speeds aloft. Surface lows will lie between 300 and 600 nautical miles north of the bold 5,640 meter contour. That becomes a critical benchmark to navigate above or below. So the 5640 isoheight marks the southern extent of Beaufort Force 6, occasional 7 westerlies in summer. What's Beaufort Force 6 and 7? There's nothing modern that needs to be done with Beaufort. It's been around for over 2 centuries. So what you need to really focus on, we're talking about 4.6 is 22 to 27 knots, occasional 4.7, 28 to 33 knots, just below gale threshold. And in the wintertime, 7, occasionally 8. 7, again, 28 to 33 knots. 8 is 34 to 40 knots. Learn the language of the sea, because the winds are intricately related to sea state, and Frank's going to cover that. So, in some areas on a 500 millibar chart, you can get up to 50% of the winds translated to the surface, and that's usually west of the trough axis or in the colder northwesterly flow, which coincides a lot the west and southwest quadrant of a mid-latitude low that has fronts that Ken talked about. That's where the coldest air is, and that's tied into the 500 millibar where 50% of the winds can flux to the surface. Okay, this isn't you, but I got my jacket. I flew here with my APL China jacket. You wind up in port, and Bob Kimball can certainly attest to this. Kathleen Frail can attest to this. In the words of Ricky Ricardo, there'll be some splaining to do. Every mate on board is going to have to say what they knew when it came to weather. So I think they're still trying to settle up on the claims, which I heard figures of a couple $2 billion. That seems high, but I don't generate that kind of rumor. That's what I heard. But there were over 1,000 containers damaged or lost. Fortunately, nobody lost their lives. So this is the track line of the APL China, Taiwan to Seattle, straight run line. This is where the APL China lost power, right in the heart of the Pacific. A little bit above a rum line and south of a great circle, actually the average route of a lot of commercial vessels in transit from one coast to the other. This is the 500 millibar where the APL China lost power. As we teach here at MyTech, the Star Center, and I try to make available through recreational courses such as 7 Seas U and boat shows, this could not have possibly been in a worse position for a ship to be. Could not have been worse. Of the whole entire Pacific Ocean, this is where the ship was. So I blow it up. This is on the divergent side of the trough, and I'm going to review you with that in a little bit. I just wanted to show that all the ship had to do is be a few degrees south of the 5640 line, and none of this would ever have happened. The good old days. Bomb. I like that word. I'll tell you why I like it. Do you have to be able to read a chart? You see that 4-letter word? We know there's a lot of 4-letter words that mean other things. That's not good, is it? You didn't have to read a chart to know maybe you ought to stay away with that, stay away from it. Well, we don't use bomb, but I'm vindicated because now it's in Bowditch, thanks to Joe Sinkowitz, who wrote a little segment on meteorological bombs as part of the latest version of Bowditch. So rapidly developing, rapidly intensifying is today's chart. So I made it very clear the good old days of good artists, bad artists. So you got a lot of flexibility in what you wrote in terms of what message you want to send to the mariner. So again, the tracking of this meteorological bomb shows that this ship was not in a good position and should have avoided. They had 5 days to make a correction. They didn't. So this is the old days of just wave heights and primary wave direction. Today it's wind and waves. Where in the place in the Pacific do you not want to be? This is another definition of storm chasing. Okay, you don't get away with any presentation I do sitting back with your hands folded. I'd like to ask you a few questions to see if you're retaining anything. Is that fair enough? All right, so 500 millibar lines are called. Give yourself a pat on the back. Anybody ready to take over? You guys are pretty good at this. All right. ISO heights are lines of equal elevation. See, you got caught up in that trap there. How high is the isoheight contour labeled 564? You got to add a 0 to 5,640 meters. Okay, how are we doing? All right. The isoheight contours on this section of a North Pacific 500 millibar chart shows an upper level what? Ridge. Now the symbols aren't used, but you have to, use your noggin and recognize cyclonic, anticyclonic. Cyclonic around a trough, anticyclonic around a ridge. Cyclonic around a low, anticyclonic around a high. Oh my. So, my goodness, I'm going to have to get to the cutoff low pretty quickly here. All right. This 500 millibar level trough, and I don't think I just tell you, we look at trough energy in terms of upstream winds versus downstream winds. If the winds are stronger upstream, that means you're going to have an amplification of the trough. That means on the divergent side of the trough, you're going to have a low pressure development. If they're stronger east of the trough, that means the low is already maxed out, reached its occluded stage, and is going to weaken. So in this case, your visuals should probably show you that the winds are slower west of the apparent trough axis, somewhere in here. Jet streams, fast winds at high altitudes, speeds of 50 knots or more. And this is pretty good, this showing this tube of air. Each sleeve represents some kind of wind velocity, and you go inside that is where your jet stream maximum is. But you know that jet stream can reach winds of over 200 knots, and again, we're not talking about the surface here. Our frame of reference needs to change when you're dealing with upper levels. Now, the jet stream can be hundreds and thousands of miles in length, can circumnavigate the globe, but it would be rare to have a jet stream continuous throughout the globe. Because what do you need to have winds to qualify as jet stream again? 50 knots. So it can be on a flat surface looking down up to 800 miles wide, maybe wider, and over half a mile deep, maybe even a couple miles. So the jet stream has dimensions horizontally and vertically and can circumnavigate the globe continuously. Generally, it will flow from west to east. So winds in the jet stream exceed 50 knots. So Google jet stream, you might come up with something like this. Everybody shows this big arrow that represents a jet stream. And what do you see? Cold air on one side, warm air on the other. Ken talked about air masses, and fronts are boundaries that separate air masses. You might call this an upper level front, but I don't want to, because the core of winds that are strong here are the result of temperature differences and density differences, and that equals pressure differences. When you're dealing with isoheights, it would be isoheight differences. The two jet streams that circumnavigate the globe in both hemispheres, the polar jet stream, higher latitude, the subtropical jet stream, lower latitude. So, the two main jet streams, the polar and subtropical jet streams. And this isn't virtual reality, but you know that there's so many sites that show the perpetual wind in motion. So this would be the very dominant polar jet stream indicated here. Then you have the subtropical jet stream. Often they're separated, and here's the deal. When you get the polar jet stream and the subtropical jet stream together as one, and you can't tell the difference, then you have headlines the next day. Storm of the century, and we're up to what, 1,029 since March of 94. I mean, every other week is a storm of the century. Here's the deal. The two streams of air really create energy, lots of energy. So you have the polar jet stream at higher latitudes, the subtropical jet stream at lower latitude. What happens when they merge? Look at the wind velocities. They really increase when the two jet streams are merged. All right. Winds in a jet stream are typically 50 to 200 knots. I got to go fast now. Two jet streams are called polar and subtropical. Upper level troughs and ridges. Okay. Long waves dominate the hemisphere, usually above 500 millibars. There's usually 3 to 5 long waves. The long wave troughs, if you would, often are called Rossby waves. They don't move very fast. They maintain their position because the shorter waves that I'm going to talk about briefly rotate through them. So you can look at the 300 millibar and the estimation of where the long waves are. And then we have to talk about short waves. This is where the chicken is clucking away, laying golden eggs called low pressure for a trough. You cannot get a surface low without a corresponding upper level trough. On the divergence side, this is what makes the weather world go round in 3 dimensions. So on a 500 millibar chart, you can examine how the ISO heights are curved, where the wind velocities are, and identify where the short wave troughs are. That's easy to do on 500 millibars. So that's the preferred level to find shorter wave troughs that generate your surface lows. And the upper level ridge, the surface high is going to be on the convergent side, of the ridge axis, and on the surface you have high pressure. So La Nina and El Nino are long wave patterns involving the polar jet stream and the subtropical jet stream. So the La Nina is higher, generally is higher latitude. El Nino is lower latitude, where the subtropical jet stream dominates. The polar jet stream usually is further north. So the winter La Nina pattern is quite variable. In this case, this is where Seattle can get 58 straight days of rain if the long wave pattern was between the Pacific islands of Hawaii and the West Coast. And that's an experience. That's duck weather. And here's your typical wintertime El Nino pattern. California is going to fall into the sea one day, not from the San Andreas Fault, but all the mudslides along Pacific Highway 1, where they have no vegetation to keep Jack Nicholson's home intact, and we get to pay for him rebuilding it. Upper level long wave influence what? Long-term weather. Upper level short waves influence what? Short-term weather, because your highs and lows, as Ken talked about, can be tracked 4 or 5 days from day 1 to day 5, and the Ocean Prediction Center has that capability too with their 5-day tracking. So formation of lows and highs through upper level convergence and divergence. I'm going to do this and then finish up with the flow patterns, okay? Frank, if you can give me a little slack, we can get it done here. So you must have upper level divergence, either speed divergence or directional divergence, siphons air from below, and in response, the air has to be replaced what's being removed. The air aloft is stronger, so more air is being removed than it can be replaced. Remember the impact of friction, and that's why low pressure exists, because of this upper level influence of upper level divergence. How do high pressures form? You must have upper level convergence. With the help of Coriolis and gravity, pulls the air down, hits the surface, it can only go one place and away, diverges away from high pressure. So weather becomes a 3-dimensional system, high, low, upper level convergence for highs, upper level divergence for lows. So on a 500 millibar chart, you can find out where your upper level divergence is, and probably underneath this will be surface lows. Your upper level convergence nearby is underneath is going to be high pressure. So you put this together, superimpose the low pressure and the high pressure, and you can see how the influence between upper level divergence for lows and upper level convergence for highs. Overlay satellite imagery with the 500 millibar, you can see where the clouds are. That means vertical air motion rising. There has to be some kind of 500 millibar trough involved with that. In the term of sinking air, you must have an upper level ridge or convergence that causes the air to sink. So sinking air, rising air, convergence, divergence. Question?
Where does the data come to calculate the millibar chart? Is it experimentally derived or a model based on surface?
It begins with balloon launches. It begins with collecting aircraft data that transit from one end of the continent to the other. It begins with estimating wind speeds using satellite imagery. There are a lot of sophisticated techniques. Joe might want to talk about that in terms of what goes into a forecast. So I'll reserve that for him. Excuse me. And you can look at these overlays. This is known as a blocking high, air is sinking. And here's your speed divergence. The ISO heights are spreading apart, but you go from 40, 60, 75, 80, 105. So a plume of strong winds and cloud formations underneath. The trough axis is the basis for the low formation to the right of it with a trailing cold front. And I want to finish up with flow patterns here, so I got to move along here. Low pressure systems form on the surface where there is upper level divergence and surface convergence. Vorticity. I'm going to skip this part because I got to get into the flow patterns here. I will show you one little illustration of vorticity and its impact on the surface. Otherwise, it would be hard to find the trough, but when you see the surface reflection of this is not insignificant. It shows up in the later forecasts as a little bit more an enhancement, but this becomes a compelling reason to talk about vorticity, which I don't have time to do this morning. So, let's talk about patterns as I finish up here. There are 4 basic patterns. West to east zonal, north to south meridional. Then you always have an upper level ridge or high as a block. And some of these blocks take on the Greek letter omega, so they call it an omega block. And then you have the cutoff low, which I'm about ready to be cut off here in a minute. So you examine the flow pattern, and there's usually more than one. So this is a zonal flow and a blocking ridge to the north of it. So all the energy is going to flow west to east by the thumb rules, 1/3 and 1/2 the 500 millibar wind speed parallel to the ice heights between 300 and 600 nautical miles to the north. And here is your omega block because it looks like what? The Greek letter omega. So it's going to block any weather moving through this area. It's either going to go south or it's going to try to go over it. And that may take a number of days to break this pattern down. And then you have the type of flow that's split, the polar jet stream moving north, the subtropical jet stream heading south due to an upper level blocking high, sitting on top of a closed low known as a Rex block. A closed off low is not quite cut off because it's embedded within the flow. And so that's going to be your challenge looking at these charts. Which is a cutoff low and which is a closed low? Here's your cutoff low, completely separated from the main flow. Okay, here's a cutoff low, and here's an enclosed low. This is not a cutoff, this is. Now, some of my colleagues could disagree. You can get 5 meteorologists in a room with loaded pistols, and there'll be 5 vacancy announcements after everything is said and done. So, the perfect storm, the one that made Sebastian Junger famous. He stole a message or a forecast discussion from one of the forecasters in the Boston office and ran with it. The poor guy is not eligible for royalties, and Sebastian Junger got rich because that's where the perfect storm was coined. So this is the perfect storm. Meridional high amplitude trough in the west, high amplitude blocking ridge in the east, and this cutoff low sitting off the eastern seaboard where the surface low just wrapped around for days on end. And of course, nobody knew at the time of the Andrea Gale until the movie came out. I was routing ship for the Navy in the first Gulf War, trying to get underneath this sucker, going from the East Coast to the Mediterranean to the Persian Gulf. So where do we go from here? Okay, I'm doing a webinar tomorrow at 11 a.m. You only heard 45 minutes, give or take. You want to hear the rest of the 45 minutes? Join the webinar. So I have flyers on that. Mark Brownhill, who's a proprietor of SSU, many different courses other than weather. Mark, you want to raise your hand real briefly? You can talk to him about SSU. And then my co-author. Anybody recognize this lady here? What a distinguished fellow. And from the Gatorade commercial a few years ago with the other Mike, this is my Mike. Be like Mike, so I have some of these books, and this guy is the most incredible master mariner that I've ever met. He really has perfected the 500 millibar. There's no routing service on the planet that will ever challenge him. So his story is in this book, so I wish each and every one of you fair winds and following seas, and now you can cut me off.